Right, so lesson 7, knowledge and knowledge check on expansion contraction. The unit of density is the kilogram per meter cubed. Write the equation that links density, mass, and volume. You've got the density is equal to the mass divided by the volume. Okay, you can use the symbol rho for density if you wish, but density is mass divided by volume is fine. Equation for weight, remember we need to know all of these equations. Okay, you will not be given them in the test. W equals mg, weight is mass times gravitational field strength. From last term, you've got the equation for pressure is equal to force divided by area. Equation for work is equal to force times distance. We use the symbol S. Again, if you haven't learned these from last term, go back and learn them. Suggest why an object can float on water, because it is less dense than water. So because it is less dense than water, and leave myself enough room there, than water. Okay, so anything floats because it's less dense. Vectors, you could have lots of examples. Force, weight, which is really a force, magnetic and electric fields, velocity, right, you might have any one of those ones. And again, scalars is pretty much everything else. So I'll leave you to put in some scalars yourself. So you could have things like temperature, volume, distance, speed, anything, any measurement other than effectively the ones I've written down there. Okay, so remember, a vector is a measurement which needs a direction to fully describe it. A scalar is any other measurement which just has size. Okay, so again, check back on the previous lessons if you're unsure of those. Right, so today's lesson, what we're looking at, this idea is expansion and contraction, and why things can expand and contract. So it all goes back, again, all this is building up for previous books, previous work. We'll build on those all the time. So if we look at our kinetic theory lesson, which is the last book, 7b, in line 6, in lesson 3, line 6, we've got the idea that solids, liquids, and gases are made of tiny particles. So just a quick recap, if we look at our particle pictures that we had, so you could have a solid, particles closely packed together, okay, just vibrating on the spot. And then you had the idea of the liquid. The particles are randomly arranged, okay. So they're randomly arranged. They're all actually touching as well, so those gaps shouldn't be there really. Okay, so the particles are randomly arranged. And then you had the idea of your gas, where the particles also randomly arranged, moving very fast and big spaces between them. So that was just what our kinetic theory told us from before. So if we look at solids, obviously I can't do this bit here where you get up and represent the particles in a solid, but when we heat an object up, okay, the word kinetic, if you think about it, what does that refer to? What type of energy? We referred to this when we done our energy module. So kinetic meaning movement. So all of this is based on the movement. So the particles in our solid, liquid and gas, they're all moving. So in a solid, they're vibrating on the spot. They just move on that spot. They vibrate backwards and forwards, left, right, up, down, but they always come back to the same spot. Whereas the liquids, they're moving around all over the place, and gas is flying at high speed. Okay, so solids, the particles are vibrating. That is energy. When we heat those up, those particles vibrate more. If you think about trying to stand on the spot, how much space do you take up? Then try and jogging on the spot, with your arms and your legs moving, you will take up more space because your arms and legs are now moving. Same thing happens with the particles. When we heat up an object, the particles in that solid object will vibrate more. They will move around more. They have more kinetic energy. So that means the particles, if we look at a low temperature solid, what we're indicating here is the circle indicates the particle, and the bracket is supposed to indicate that they're actually moving. So the particles in a solid, you don't need to fill the entire box up. The particles in a solid are vibrating and moving. As they vibrate, they move backwards and forwards, take up a little bit of space. When we heat them up, they vibrate more, or they have more movement, i.e. they have more kinetic energy. So I'm indicating this by the fact that I've got 3 brackets around them, because they're vibrating that distance now. And even just drawing in 3 brackets around these particles, you can see they actually take up more space. Okay, because the particles are vibrating more. Because of that, they take up more space. It's like in the corridors in school at break time. When people are moving around, it gets very, very packed. Not these days, of course. Whereas if you all just stood still, there'd be gaps between you. But as you're moving, you fill up those gaps because you're vibrating. And as you heat the particles up, they vibrate more as compared to this one, only a little vibration. So the amount of space this particle takes up when it's vibrating is that amount of space, whereas the particle vibrating more, because it's got more energy, takes up that amount of space. So you can see the amount of space by the particle taking up vibrating more because it's hotter, it's higher temperature, is greater. And that basically means, that basically means that the solid gets bigger because its particles are now taking up more space. Now, if you look at a lump of metal or anything heated up, you don't actually see it getting bigger. It's not going to take up that much space. You can physically get twice the size or anything like that, but it does expand because the particles are in the molecules, or sorry, in the solid, are all vibrating. So these molecules are vibrating, so they take up more space. That means the solid has to get bigger itself. Okay, now we can't see that visually by a straight observation, but in the lesson, again, I'll go to the share screen. All the experiments in the lesson are those experiments 1, 2, 3, and 4. So, okay, so have a look at those after I've done the recording, and then I want you to fill in your observations of what is happening. So this first one, a ball and hoop, as you see, is a metal ball, a piece of brass, a solid piece of brass, and we've got that fits through a brass hoop, and we can pass the hoop through the ball through the hoop. Okay, I want you to describe your observations when the ball was heated in the Bunsen flame from step 3. So what I've done in the video is heated up the solid brass ball, okay, and then try to pass it through the hoop. So I want you, in each case of all of these, to write in your observations. So step 1, look at the video. Describe your observations when the ball was heated. So what happened to that ball as it went tried to go through the hoop, okay? Describe your observations as the ball is cooled in step 4. So the ball is then put into some cold water, and what happened in the video after that happens. Write in your observations there once you've observed experiment 1. Experiment 2 is something called a bimetal strip. There's an explanation of what that is in the video. Basically, it is a piece of brass and steel that are bonded together. So on one side of this strip is a piece of brass, and the other side is steel. So basically, it's 2 metals stuck together like this. Okay, so this one says steel, and this one is brass. And what happens here is the brass will expand at a greater rate than the steel, okay? But they are stuck together. So if this one gets longer than the steel, that can happen. So the only way that brass can get longer than the steel is if it curves. I'll exaggerate the curve here. And what happens is when the bimetal strip is heated, it gets bigger on one side. So if you measure the distance from there all along that line to there, that distance is greater than the distance all along the black line here to there. Okay, because the outside of the curve takes a bigger distance. You can probably see visually that that outside line there is longer than that one there. So this one expands more than the steel. Okay, again, place to mind, we're going to show you in the video, it is in some ice. Look at describe its shape in ice. It's not as dramatic in ice as it is in the metal, because the difference between room temperature and the ice is only about 20 degrees. Sorry, in the Bunsen flame, the difference is about 200 degrees. Okay, so again, watch the video, describe what happens to the bimetal strip in the Bunsen flame. Okay, if you've got any questions on any of this, yes, there is going to be a video. The video is on the SharePoint page, as I've just shown you. Again, I'll show you again at the end. Experiment 3 is liquid. So that is experiments 1 and 2 show you the expansion in solids. Experiment 3 is showing that this thing also happens in liquids, because in liquids, the particles vibrate more and take up more space. So I'll have a flask, which has got a capillary tube, which is basically a very, very thin tube. That's filled with dyed green water. Okay, and then it is moved from ice into warm water. Again, describe, once you view the video, describe what happens when the test tube is moved from ice to warm water. But now, I've done it here, left 2 spaces for it, but you only really need 1 space, because I actually, when I've done it in practice, it didn't really show much unless I moved from ice to warm water. So you use one of those boxes to put your observations in there. And experiment 4 was basically, I took a round bottom flask, basically put my hands on the round bottom flask, upended it into a beaker of water. So there's again a capillary, you will see once you see the video, and then what happens, observe what happens on that one. And again, write your observations in this box here. Okay, so those 4 experiments on the SharePoint page. Again, since somebody asked, I'll just show you on the share screen where that is. Okay, so that's experiment 1, 2, 3, and 4 on step 3 on the SharePoint page. Okay. And the effects then of this expansion and contraction. So basically, when you heat a solid, liquid, or a gas, the solid, liquids, and gas will expand because the particles have more energy, so therefore they vibrate more, taking up more space. The effect of that is important. One of the reasons to study this, because there's very real effects on this on buildings and so on. So when a hot day, a building expands. Okay, the Eiffel Tower, for example, expands by about 27 centimeters during the day because of this heating effect. Actually, no, sorry, the 17 centimeters in the summer because of this heating effect. Bridges, which are made of steel and concrete, they expand, but if they expand, there's no space for them to expand to, because they have a start and an end point. So they have to be designed to allow this expansion to take place. Otherwise, the road on the bridge would buckle and break. So in bridge design, they built in expansion joints. There's gaps between great big lumps of steel that can go in and out. Wires on electric wires bringing electricity to your houses, if you ever notice, they lag, they bend down. That's not because the wires are particularly heavy. It is because during the hot days, the wires will expand, so therefore become looser. But on colder days, like now, they will contract. They will do the opposite. And if the wires were built when they were put up were very tight, on the cold day, if they contracted, the wires would just snap. So they have to have a loose, they have to lag down, they have to be loose to allow that expansion and contraction to happen. Okay, bridges often have rollers on them. They're actually built on big rollers, like wheels effectively. So when they do expand, they can move. So all our buildings are designed to allow for this expansion and contraction and the heating. Otherwise, the buildings would crack and fall apart. Okay, so when you view those, try the knowledge and application questions.